So here's our first example. We're going to take the partial derivatives, plural, of the function z equals f of xy equals x squared plus 3y squared. Once we do that, we're going to find the actual numerical values of those derivatives at the point 1, 0, and then try to explore what they mean. So let's go ahead and take a look at this example first, and then we'll build up the examples in their complexity moving forward. Okay, so notice that we have the screen split into two pieces. That's because we're going to compute each of the two different partial derivatives one at a time. So let's go ahead and start with the partial derivative with respect to x here on the left. F sub x is the notation that we're going to use. We'll start with the first term, x squared. So the derivative of x squared, as we know, is just 2x. So that's pretty easy. That's pretty straightforward. Nothing new there. We haven't changed any of the rules. The derivatives are still going to be computed in the same kind of way that we saw before. Now for the second term, 3y squared. If you saw that back in topic 4 or topic 5, you would say the derivative of 3y squared is 6y. But that assumes that y is a variable. Remember, since we're taking the partial derivative with respect to x, y behaves like a constant. So 3y squared looks like 3 times some constant squared. Doesn't matter what that constant is. A constant squared is just some other number. It's another constant. And then when I multiply that by 3, I get yet another constant. So 3y squared is behaving as though it were fixed and a constant. And so therefore that whole thing has a derivative equal to 0. And that feels non-intuitive at first, but the key point to remember there is that y is behaving like a constant, so 3y squared as a big huge chunk there is itself a constant, and the derivative of a constant, as we know, is 0. So the partial derivative with respect to x is 2x. Now let's go over here to the other side and take the partial derivative with respect to y. So when we do this, when we look at the partial with respect to y, the very first term, x squared, has a derivative of 0. Now let's stop and make sure we understand that. We're taking the partial with respect to y. So y is what's allowed to change. Y is the variable here. Every other independent variable, in this case x, behaves as though it's a constant. So when we took the partial with respect to x a minute ago, x was changing. Now x is not changing. X is no longer a variable. X is a constant, so x squared is also a constant. So the derivative of that first term is 0, and now the second term, 3y squared, is no longer behaving like a constant like it was in the previous partial example. 3y squared is now a variable term because we're taking the partial with respect to y, therefore y gets to change, y is the variable. So the derivative of 3y squared is, as we already know, 6y. So the partial derivative with respect to y is 6y. Now, most of the examples that we'll see are not quite this clean or easy, where one of the terms just goes away, but it's designed to give you a quick introduction into how partial derivatives behave, and in particular, to get you to think about how to focus on the variable that you're taking the partial with respect to. Everything else you have to think about as a numerical constant. So now that we know the partial derivatives, we can now compute the value, or we can evaluate those derivatives at specific values of x and y, or at specific points on the surface. So recall that the partial derivative with respect to x was the expression 2x. And if we want to look at the value of the partial at 1, 0, when x is 1 and y is 0, then we plug in 1 for x, and we plug in 0 for y. So 2 times 1 gives me 2. We don't have a y here, So there's nothing to substitute. That's not always going to be true, but in this case, there's no y, so we don't have to worry about substituting that 0 value. So the partial derivative with respect to x has a value of 2 when x is equal to 1 and when y is equal to 0. So what that would mean visually is that if you were on some surface, if you were to visualize this x squared plus 3y squared surface, which is like a paraboloid, and started to move along that surface parallel to the x-axis, starting from the point 1, 0, your y value would stay fixed or constant, but your z value would go up by about 2 units. The slope of the tangent line at that particular point on the surface would be about 2. So you're moving along the surface, you're staying on some surface, but your movement is constrained so that it's parallel to the x-axis, then your total climb in the vertical z distance will be 2 units. Now if you look at the partial with respect to y, which was the expression 6y, and then substitute 1, 0 into there, so x is 1 here, but there's no x, so there's nowhere to substitute it. Y is 0, so we can put that in. 6 times 0 is 0. So there we have no change at all in the z direction. So if we move on this surface parallel to the y-axis by 1 unit and we force x to stay fixed, then the z value goes up 0 units. It doesn't change. The slope there is 0. So this is interesting because you have 2 different slope values at the same point, but each one is computed by envisioning yourself moving in one of either the x or the y directions. As you move in one direction, your z value is actually changing, it's going up. If you move in the other direction, the y direction, your z value isn't changing. So sometimes you'll have positive values for your slope, sometimes negative, sometimes 0. You can't tell until you actually take both of the partial derivatives, plug in the numbers, and actually see what's going on.